Okay, hi all, welcome to the quiz seminar. It's our last one, so let's enjoy it as much as possible for this semester, hopefully. So, we have the great pleasure to have here today Chen Lung Hung from Purdue University, Associate Professor at the Department of Physics at Purdue University, and he's an experimentalist in platform simulator. So let me say a few words about his academic steps. So Chen Lung did his Bachelor of Physics in National University of Taiwan. Then he moved to the University of Chicago for doing his PhD, where he remained for 1 year as a postdoctoral scholar at the James Franck Institute. Then he moved to Caltech as a postdoctoral fellow at the Institute for Quantum Information and Matter. And then he moved to Purdue as an assistant professor in the Department of Physics, where he's now an associate professor. So his research interests revolve around quantum simulations using ultra-cold atom platforms and nanophotonic devices. So he's interested in emergent phenomena with many body systems, engineer novel quantum materials using cold atoms, and non-equilibrium dynamics in many body systems with strong correlations. And on the other hand, he's doing also experiments in nonlinear quantum optics with atom nanophotonic hybrid systems to study topological quantum materials with strong light-matter interactions and applications to quantum communication and sensing. Thank you very much for being here today. We will hear about self-patterning in a dilute gas of 10,000 atoms. We're very much looking forward to your talk. The stage is yours.
Thank you very much for the invitation to give this short talk. I'm going to talk to you about an experiment done in my group, several experiments done in my group, but basically they are all kind of under this kind of a phenomenon, let's say, self-patterning. And so I call it a dilute gas of 10,000 atoms. So you may wonder, is it really that small, right? Yes. So this is really, you can see that. So these are sample images, 3 different images coming from individually coming from a group of atoms on the order of 10,000 atoms. You see the kind of a brighter ones, that means density distribution. You have higher density in the middle, and black means no density, right? And the reason you don't see single atoms because we use optical imaging, and then our imaging resolution is only 1 micron, so we will not be able to see single atom, but you see a distribution. Okay. So what you are seeing here, some kind of 4 dots in the middle. And then here you see 2 dots grouped together and two groups like being separated a little bit. You see very similar image, but kind of oriented with different angles. But these dots are actually vortices. So these atoms are actually superfluid. And inside the superfluid, you have these vortices. One with circulation, say clockwise, and the other one counterclockwise. So these are vortex anti-vortex pairs. And they come out in pairs and they come out like this way, opposite direction. And so these states are generated spontaneously, all from a very simple step. What we did is just we have a bucket, we hold the atoms, and then we just stop it, shake a bucket a little bit. And then some insurance dynamics generate this kind of very interesting pattern. So I'm going to tell you one story I'm going to tell you is about this. Okay, so pattern formation is ubiquitous in nature. You see it in a lot of samples. For example, you kind of heat up a bucket of fluid. You may see this kind of formation, this very interesting geometric patterns. It's coming from the Bernard instability, very famous instability. You would also see, like, if you have a kind of a wind blowing slowly across sands, actually create sand ripples. And what happens is that this some sand get picked up, and by the time get picked up, it becomes too heavy to drop down. But somehow you would form this kind of pattern with specific periodicities. You would see that part. This is the spot on the animal first on that part. for this very beautiful pattern. And you could even like going to the kind of a scale, large scale structure of the universe. You can also see this kind of cosmic wave-like thing. These are kind of the distribution of this clusters of galaxies, form something like this. And so all these pattern forming things in nature, especially let me say it's classical systems, typically you would have come up, would develop inside an otherwise uniform system. You really don't have any special pattern or anything. You just have some initial randomness. But somehow there is some instability in the system. They would like to promote certain patterns. For example, in the initially, the universe is just a hot, cosmic soup, but gravitational instability would like to cluster galaxy together form this kind of web-like thing, right? So instability would like to pick up certain length scales, certain geometric patterns, certain shapes, certain excitations, grow it exponentially, right? And eventually we lead to pattern formation. But of course, at a certain stage, some other effect will kick in and then stop. And so Alan Turing in 1952 kind of was the first to come up with some kind of mathematical model to explain what it means by pattern formation. He was thinking of a very simple system is that he was thinking about, I have two chemical substances. Each of the substances they will want to grow. They want to grow their column. But the thing that he added in, one of the things is that he said that the presence of one chemical substance somehow could exhibit the growth of the other chemical substance. That's the only thing that he did. And then it turns out that with this very simple so-called reaction and diffusion model, so diffusion is they want to grow, and then reaction is like inhibition due to the presence of the other chemical substance. You were able to kind of observe all these very interesting patterns that looks very similar to some of the animal patterns that you can see in the previous example. And so this is kind of one of those first models to explain pattern formation. And in this talk, I'm going to tell you that even for like in quantum mechanics, even for a Schrodinger equation, once you add some nonlinearity in there, you would also have this kind of pattern formation. So I'm going to tell you what that is. But where's our diffusion, right? So for example, this kind of kinetic energy term would like to make the wave packets to disperse, let's say. And on the other hand, we have this reaction, right? Basically, the nonlinear interaction it could be attractive. So basically, making the wave would like to keep increasing its amplitude, or being repulsive, like having too much amplitude will surpass the growth of the amplitude. But anyway, so you have this, you can also kind of feel it as some kind of reaction diffusion. But anyway, so this nonlinear Schrodinger equation, as I will show you, will also give you very interesting self-patterning models. Right, so where's our instability, right? So in this instability comes from that you have some wave function, and then add to that wave function some small perturbations. And so this small perturbation, then we call it delta phi. And then with label by k, so k typically can mean a wave number, okay, or momentum factor or whatever, in certain pattern. And so you can perturb that, and then you could obtain the energy spectrum as a function of k. And instability occurs when you find that the spectrum is actually imaginary. When you have an imaginary spectrum, that means that things start to grow exponentially. And this is your instability. So I work with the dilute gas of cold atoms and cool such as is in the so-called quantum regime. And so such that I can study this coherent pattern forming dynamics, not just the kind of things that you see in nature, although the kind of the underlying mechanism looks very similar, but it has some quantumness of it. So if you start here in the quantum system, your initial perturbation is no longer just classical noise. It can actually be quantum fluctuations. And so instability will take your quantum fluctuation, amplify it, And so if you start from the initial state, very low temperature, zero entropy, and then you start to grow some pattern. This pattern is by itself also some kind of order. And more than that, it could have some quantum entanglement there. I would say what that is, right? Of course, this very good thing doesn't last forever, right? So at some point, some other effect will kick in, some other loss effect will kick in. Eventually, our system may fragment, may dissipate. There will be particle decay, or other kind of things happen, and eventually we get this sort of final state. But I just want to say that this kind of instability, especially generally we call it dynamic instability, actually is used as a resource, because whenever you want to grow something from your system, in order to conserve, for example, conserve momentum, then the wave that's been generated has to come out in pair, right? So you have a conservation of momentum, or if you say I have generated some particles, the particle has to come out in pair, right? And so we call this, give you a name called pair production. Pair production in quantum systems can be triggered by instability. Actually, it has been observed and studied in trap ions, quantum gases, or even in quantum optics in entangled pairs. And this is used as a resource to generate entangled particles. Okay. All right, so my experiment is 10,000 ultra atoms. They form a quantum fluid. And you see a lot of quantum fluids, like all the way from neutron supercritical in neutron star that happens at 10 to the 9 Kelvin, all the way to the bottom here of the arrow here. We deal with nano Kelvin range ultra atoms. Okay, so here there's also like happening at around 1 Kelvin. You have superconductor junctions. You also have superhelium happening at around millikelvin. Okay, so we work with the dilute gas of atoms. The reason we want it to be dilute is that these atoms we don't want them to get too close to each other, because once they get too close to each other, they will form molecules. They will just become, right? They will release tremendous energy. So we don't want that. We want that to remain their pristine condition, single atoms colliding with each other with elastic collisions. That's why we keep their density modest, about 7 to 9 orders of magnitude thinner than air, right? But in order for them to exhibit quantumness, it's necessary to cool to this kind of temperature. So we do this by first perform the so-called laser cooling using the so-called optical molasses technique, cool them to the microkelvin range. And then for the last step, we use the so-called evaporative cooling, just like you have a cup of coffee and then you just put it there, that hot water molecules leave the surface, take away energy, and then this water goes down. This the same thing here. So that hot atoms leave the trap, and eventually we can reach the actual temperature. Okay, and so to give you a better idea how this quantumness means, it means that at around like microkelvin temperature, the wave nature of particles start to appear. Here you are seeing this kind of a de Broglie wavelength, roughly, starting to get larger, but still small compared to the interparticle separation. But once we cool the temperature of the system down to the nanokelvin range, the interparticle separation and the thermal de Broglie wavelength becomes comparable. This is when we end up with a gas of atoms that all occupy, in the case of ideal gas, all occupy the same wave function and the inside-out trap, right? But no, in reality, it's not that simple. These are not just non-interacting particles. These atoms actually interact with each other. But since that we are in such a low temperature, it becomes relatively easy to describe how these atoms interact. If you study quantum mechanics, you know that to study collision, only thing is needed to low energy collision. One thing is needed to describe the collision is called the X-ray scattering event. So basically, the X-ray scattering is a length scale that pretty much tells you the cross section. So how strongly these atoms collide with each other. This X-ray scattering can be positive. It also can be negative, depending on the collision location. Luckily, in our system, we can actually tune it by a mechanism called flash resonance. Basically, we can basically, it's very simple, just adjust the background magnetic field. We can bring some foreign molecular state to interfere with the freely colliding atoms to change the collision phase. Therefore, we can tune the scaling length from positive to negative. Okay. So this is all you need to know about the interaction between atoms. So once we cool these atoms down to the nanokelvin range, and then prepare them in positive interaction. That's what we, moderately positive interaction that form superfluids. So what you are seeing here is there's 10,000 atoms trapped inside a box. So this is literally this atom, the density distribution fill this entire box. This is a square box. And this is the average image. So we repeat the experiments many times, and then average the density. This is what we see. In fact, in each of the single experimental realizations, this is what we actually see. So in some portions, you will see slightly red. That means slightly higher density. In some portion, you see slightly dark, brighter. That means lower density. And what does that mean? So you have some density fluctuation. And what are these excitations? These excitations are phonons. And it's very important. I will come back to this phonon later. We could also kind of put in a single quantum vortex inside a superfluid. What you're seeing here is a circular superfluid, and we have a quantum vortex. A vortex basically means that the wave function has a 2-pi phase winding around the vortex core. And so in the middle, because you have a phase defect in the middle, and then it's necessary for the density to go to 0. That's why you do not observe density right in the middle of the quantum vortex. Okay, so how do we prepare the system? So we prepared the atoms in the box by optical potentials. Okay, so what we have here, I say 10,000, but sometimes we prepare out to 30,000. These atoms are alkali cesium atoms. And so it's prepared in the all repulsive potential. That's how we can make the box. So in the vertical direction, this potential is formed by a laser standing wave pattern. And so it's a repulsive force to the atom. So atoms would like to stay at the node of the standing wave. Horizontally, we use high resolution microscope objective to project also repulsive light to confine the atoms inside this kind of repulsive wall. So for example, this is a circular wall, right? And so to observe the density distribution of the atom in the box, we send basically a resonant light from beneath the atoms and through the plane, they get confined, and then we use a CCD camera to record the shadow cast by the atom. From there, we can know the density distribution. So because the very tight confinement coming from the, we call it optical lattice. So very tight confinement coming from the optical lattice. Basically the atomic motion along this vertical direction is frozen to the ground state. And any perturbations that's appearing in the gas will appear in the 2D gas. So we call this as a quasi two-dimensional gas, and it's confined in a two-dimensional box. The interaction strength take the ratio between the scaling length and the harmonic oscillator length along this vertical direction. Okay. And this scaling length again is tunable from positive to attractive. The temperature of the gas is smaller than 800 Kelvin. And so once we take an image like this, these single atom images blur to a spot size of about 1 micron. And so basically we can pattern some light, even a produce P, and then combine the atom within this box like this. And but we can also use some arbitrary drifting light. We can like playing a movie, right? So kind of a pattern potential, like a tightly focused tweezer dragging across the gas to stir and then create vortices like this. Here is one single vortex, here a pair of vortices. So with this, this is the system, and then I'm going to kind of discuss about three pattern forming instability that's pretty classic that have been discussed across many different disciplines like nonlinear waves or other physics. So first is modulation instability and how it creates quasi-particle and entanglement. And the second is the so-called snaking instability, and that's responsible for creating vortex pairs like the first slide that I discussed in the first slide. And the third one is the lambda instability and self-oscillating flows in the supersonic. Okay, so first modulation instability, and so what's been unstable? In modulation instability, the things that are unstable are phonons. So this is an energy dispersion of a phonon in an interacting gas. So K is the momentum wave number, and N is the density of the gas, G is the atom interaction, right? And so when interaction is positive, then at low momentum, this energy dispersion is just proportional to K wave number. So you have a linear dispersion, that's why we call it phonons. So at low momentum, you have this almost linear dispersion. But the problem is that once you quench the atomic interaction to attractive, and it turns out that this entire energy dispersion becomes imaginary for a certain range of small momentum, right? So you will have at negative interaction, the energy dispersion becomes imaginary. And I already conveyed to you, once you have imaginary dispersion, you would start to grow these perturbations. And then the one that has the largest growth rate will have the largest imaginary dispersion. And so it's correspond to square root of 2ng. And this turns out to, we call a length scale related to the inverse of this, we call it the most unstable length or the heat index. And so if we prepare initially a superfluid sample like this, and then quench the atomic interaction and attraction, you start to see a lot of density wave flowing in the gas. Okay? And so if I prepare initially a very elongated gas like this, and then quench the interaction, at the same time remove the horizontal confinement, I see that I start to see a lot of this kind of small circular droplet-like things forming with a specific size. And it turns out that this kind of cell form thing is called tonsolaton. Okay, you may have a soliton in nonlinear optics. It almost always happens in one-dimensional systems. That's because in 1D you could have formed stable solitons in the nonlinear Schrodinger equation like this. But in 2 dimension, it's very difficult to form solitons because both the kinetic energy term and the interaction term is inversely proportional to length scale to the square. So that means that one wants to create attraction, one to disperse the gas. It's very difficult to find a specific length scale to balance these two counteracting terms, right? So there's only one specific solution that can exist to have this kind of a stationary state, and it's called the Towns profile. It has to be very specific profile, and they have very specific atom number within this profile to form a stationary state. And another very interesting thing is about this is that since it has the same scaling in kinetic energy term and interaction energy term, this is a so-called scale invariant equation, meaning that if you can find a tonsolaton at certain length, right? If you change the size of the soliton by a factor of lambda, all you need to do is you scale the amplitude of the wave by the same factor, you will find exactly the same solution. And so it turns out that when we quench the interaction, all of a sudden quench the interaction, this most unstable mode would actually want to grow density waves that eventually fragment pieces of the gas into pieces with a size to see that circles the number of atoms that's beneath this. It doesn't depend on the density. It only inversely depends on the interaction strength. And then if you look at this critical atom number here, for forming tensile atoms, compare these two numbers, it looks almost the same. In fact, we have tested, we just prepare the gas, quench the interaction, no matter what the density times G that we have, over almost 50-fold of this scale, we always see a number of atoms sitting within this one. So it's a very amazing self-patterning coming from just from a single interaction which we can form this kind of very intricate system. So we have tried to do this by preparing first a single vortex, quantum vortex in the gas, and then also quench the attracting interaction. So what you are seeing here are the horizontal rows are the same interaction, but waiting for different times. And then vertical ones are quenched to more and more attracting interaction. So while we quench, not only density waves have to grow within the gas, also this gas, their growth also need to respect the fact that there's angular momentum in the gas. So what we are seeing here is that you start to see density wave growing, but at the same time, the center core is also growing larger and larger. Eventually, they will fragment into a necklace of soliton-like look-like things. And so if you actually look at individual density profile, individually, all these are tensile. But at very small attracting interaction, you see that the gas forms a kind of a donut shape, right? And the reason is that the unstable length scale, which is roughly the transverse size of this length scale, is no longer too small, right? And so it will not be able to immediately break down the gas. Instead, it forms this donut. And this donut actually, again, looks like a shape that's very close to one solution, also a stage-turning state solution called vortex solitons. That's basically excited tensile with one angular momentum in the soliton. And if we continue to hold this gas for even longer times, all the way up to 85 milliseconds, what's shown here is just up to 50 milliseconds. If we hold for even longer times, they start to break up, right? So they start to break up into a circular array of small solitons. And sometimes you see 3, sometimes you see 4, sometimes you see 5, roughly angled with 360 degrees divided by L. L is the angular number. And we actually try to analyze the so-called angular power spectrum by just integrate over this radial density distribution. And from there, we do a Fourier transform along this simultaneous Fourier transform and look at the amplitude of the Fourier transform amplitude. We can plot the power spectrum, angular power spectrum. We can see that at long times, you start to grow a peak. In this case, that's around 3, L equals to 3 mode here, right? And so this corresponds to the most unstable mode that would have the largest exponential growth amplitude. And if you compare this, right, so Fahrenheit, say this mode must equal to kind of the kind of most unstable wave number coming from modulation instability times some number. It turns out this number is very close to the radius, the average radius of the gas, which is about 10 microns, right? The radius of the gas, and it agrees pretty well. And so here I'm going to talk about some quantumness about this modulation and stability. And so here we are seeing that a most unstable mode is growing. But if you just look at the power spectrum of the most unstable mode as a function of time, and here at time I scale it with the interaction energy scale, then you actually see that the growth actually agrees pretty well with a hyperbolic waveform. And if you actually even think about microscopically, what's going on in this kind of growing of density waves inside the gas, by performing Bogoliubov analysis, you see that it actually can be, you can actually arrive at this kind of a pair production Hamiltonian, where this epsilon k is the imaginary of energy spectrum, and A dagger is the creation operators of collective excitation with momentum along k and minus k. So these excitations are excited in pair and with opposite momentum. And accompanying with that is a reverse process. You would have pair annihilation, basically. Two waves come in and they annihilate each other. And actually, if you ever work in quantum optics, this looks very much just like spontaneous parametric time conversion. What's that? Okay, so you have a pump laser, very high power pump laser. You shine a Chi2 nonlinear crystal. You can generate a pair of photons that's both momentum and energy entangled, right? And so in quantum optics, right, how do we know that these two photons are entangled? The way in quantum optics they do it is by taking two beam speeders, take these two photons, and then interfere these two beam speeders with a laser, which is basically a coherent field. And so at the two ports of the beam speeder, you have these single photon counting detectors. And then once you detect the signal, you either subtract them off or add them together. So if you have signal subtraction, it turns out that what you get is the sum of two operators, A dagger and A, for mole 1, and then the other one is for mole 2. If you adjust the relative phase of the coherent laser field, right? If you can control the phase and tune it, you can also measure another conjugate quadrature. Well, if here the sum I give you x, then here the difference will give you p. X and p are conjugate operators, right? So basically in this kind of XP phase space, you basically it looks like whenever you're adjusting the field, you're kind of rotating your bases, right? And so to see that there's entanglement, all you need to do is by rotating this angle, you can see the noise coming from this measurement. As long as it's suppressed below a shunt noise level, you say that is quantum entangled. But how do I understand it? Right. The way to understand it is the following. This is the kind of the density operator of the two modes. And if they are classical, they are not quantum entangled, meaning that this density operator, you can write it as a separable. They can be separable. You can write it as ρ1 cross product ρ2. And then so, and then you can perform a measurement of this kind of noise measurements. And by Cauchy-Schwarz inequality, if the density matrix can be written like this, then this has to be bigger than 4. Right? And if this thing is smaller than 4, that means that it violates this mathematical theorem. It means that the density matrix cannot be written like that. That means that the two modes are entangled because they are not separable. Right? This is how that you measure the noise like this below the shunt noise level. It tells you that you have two more quantum entanglement. So how do we test that modulation instability actually give us two more quantum entanglement? So again, let me remind you again, we quench the attracting interaction, we start to grow density waves in our gas. So this is like you have growing counterpropagating modes. And you hold it for some time, right? And then we quench back to attracting interaction. How does it correspond to quantum optics picture? So it turns out that superfluid quantum atoms, they are just like our pump atoms. So when we quench the attraction, quantum atoms collide, create pair of counterpropagating quasi particles. Okay. once we quench back to attractive interaction, these quasi-particles get converted to phonons, right? And so when we wait for some time and then do the imaging, what we are seeing is actually the interference between the phonon and the ground state atoms. It just looks like this interfering with the coherent laser. And so once we look at this density noise distribution, we can do a Fourier transform. We automatically get an operator like this. So AK dagger plus P minus K. Okay. And we have some factor in the front that's related to the interference of the ground state atom with this phonon. And so if you kind of look back to this entanglement criterion, it turns out that I just calculate the density noise power spectrum. This is my density noise power spectrum, amplitude squared divided by number of atoms. As long as it is smaller than this CK, I call it squeezing parameter. Basically, it's the ratio of free particle dispersion divided by phonon dispersion. As long as it's smaller than this number, and this means that this equation is violated, the bigger than 4 is violated. Then I show small integrity. So another way to think about it is that this SK divided by CK is basically telling you, one, this is quantum fluctuation, plus phonon number in K minus K. If they are quantum entangled, that means that they have a correlation amplitude that will change in time, that's my whole time, and then that will be smaller than 1, means that these have to be bigger than the sum of the two phonon numbers. And so in our experiment, we quench the attractive interaction compared to a few different situations with modulation instability, no modulation instability, and with 1 millisecond and 2 milliseconds. We can see that with modulation instability, our initial fluctuation is large, and then it will then after holding for some while, it will go down and then even below 1 for some of the K factors, and then it will actually oscillate in time, but gradually get damped because of some kind of imperfection in our experiments. But what we are seeing, if we keep looking at the minimum that we can achieve, we can see that once we quench the attractive interaction for a certain amount of time, we can actually achieve quantum entanglement, because this inequality is violated. The minimum that we can see is that it can go down to the smallest 0.8. Okay. And this is how we show that these two modes are quantum entangled. And I think this is actually quite interesting because this is kind of also related to EPR paradox. But now it happens, EPR paradox happens for photons, but now it happens for phonons. So let me remind you. So I have created two entangled particles, and I send it to Alice and Bob. So this is the way I can write down the entanglement. So phi or phi are different bases for Alice, and U and V are different bases for. This is the other way around. U and V are different bases for Alice, and the other way is for Bob, right? And so if these two particles are really quantum entangled, means that depending on the choice of bases Alice choose, right? She can choose to measure, say, in the basis of U, and depending on measurement outcome, she can immediately know what the measurement outcome of Bob's would be. And this actually is a very interesting situation. It's called steering. Basically, that means that Alice could actually manipulate the outcome of Bob. All she needs to do is pick a basis, do the measurement. Seeing that, she will immediately tell that Bob has this outcome. And this, of course, requires not just the two more entanglement squeezing that I have shown you. Actually, it requires that this to be smaller than 0.5, which we call it Heisman limits. We are not there yet, but we are working towards realizing that. So how do we kind of test this kind of EPR paradox? So one can imagine that we could have a elongated quantum gaps, and then we try to locally modulate, say, the interaction. So we can generate entangled phonon pairs. And then it will propagate to two different regions, separate regions, Alice region and Bob region. And if you individually measure the noise, just like what I did, measure the noise in this region, individual regions, you will see that, oh, I will have increased noise. It seems like the noise keep increasing. So my gas must be heated up. But in reality, if you actually look at the cross correlation between noise in region A and region B, you could actually see that it would tell you this operator, the measurement of this operator, and that should not be zero because they have their common origin. Right? So this could, in principle, realizes a EPR pair of phonons, electron gas coming from the modulation instability, and also give us some very interesting kind of phonomization, meaning that if you just measure one part, it looks like temperature is increasing, but if you actually look at both of the systems, then in fact, this is the quantum integral system. All right, so I kind of spent a lot of time, so hopefully for the rest of the probably 10 minutes-ish, I can very quickly go through the two topics. So the second one is talking about topological defect formation and staying instability, so which is related to the experiment that's done in the first slide. So in this experiment, we prepare the atoms in a circular box, and then here we always stay at repulsive interaction, okay? So they form stable superfluid. But what we did is that we all of a sudden shake the box a little bit by suddenly lower the box wall. It's like this. So we lower the box potential. Effectively, it looks like we make the box size a little bit larger. What will happen is that this superfluid will want to expand outward, but they will need to be reflected by the wall. And then these kind of superfluid will need to interfere with itself, and then create interference fringes. It turns out that these fringes can actually create soliton. But in this case, it's not a bright soliton. In the previous case where we have high density, it actually creates solitons where you can have regions of low density. It's called dark soliton. So dark soliton is actually, if you look at the phase profile, it has a pi phase jump. Okay? And because you have a phase defect in here, so density necessary needs to go to 0. And the size of the soliton is related to the heating method. But you can also have the soliton not being so dark. In this case, it's called gray soliton. You actually don't go all the way to full contrast. In this case, the soliton is actually moving. Okay, and then the phase gradient is not completely pi, finite number, and the width would also change a little bit. And so in doing this experiment, from simulation, we can see that the edge started to generate this kind of gray circle because it's a circular shape. You will have this circular symmetry, and then you want to travel to the center, and then it gets darker and darker because you kind of have to conserve the energy. Therefore, you start with gray soliton, become very dark soliton, until some point it cannot shrink anymore because your depth cannot go negative, right? You cannot shrink anymore, then you would have to bounce back out. So you will see this kind of a bouncing ring dark solitons. In experiments, we can actually see this, right? A very similar behavior, except that at later times, you can actually clearly see that the shape is distorted, and then eventually this kind of dark stripe break up. In fact, if we release our box, allowing atoms to kind of perform time flight, it turns out that these dark stripes are actually two separate holes. And these are the anti-vortex. And this is the instability. This is, again, classical snaking instability is in action. Basically, what it says is that when you have a dark soliton in dimension higher than 2 dimensions, 2 or higher dimensions, they are unstable against transverse perturbation. What you see is that it will start to grow, this wavy-like behavior, and then it will get bended too much that eventually it will break up and then form pairs of vortexes of opposite circulation. For ring dark soliton, it has long been predicting that if you start with a ring, eventually it will break up into pairs of vortex and anti-vortex pairs. However, this had never been observed experimentally before we actually performed this experiment. And so one of the very interesting things is about the size of the instability band. because this ring soliton is a soliton that wraps back to itself. You only have so many number of unstable modes that's actually proportional to the radius divided by the width of the soliton. So when the soliton shrinks down, the instability band actually would actually the soliton will get deeper and deeper. And then one interesting thing is that the instability band would actually go larger and larger. And so when the soliton shrinks down, it gets deeper and gets more and more unstable and starts to distort. And that's basically what we observed in the experiment. So if we were to keep track of the density perturbation around the soliton while it shrinks, and measure the kind of a simultaneous density correlations, that's how it's the correlation of the perturbations as time goes by, you can see that at some point, it has very strong two peaks coming out that's separated by around 100-degree angle. That means that you have a L equals to 3 moles that's developing. So this is why you see all this kind of triangular shapes. And then, but in later times, this mole disappears. And in fact, it becomes L equals to 2 mole dominant. That's how we kind of see that this soliton eventually, once they kind of bounce back, they break up into 2 stripes. Okay. And so we could actually also do a Fourier transform of this kind of a simultaneous density correlation function. And so what it tells us is the amplitude of individual angular modes L equals to 2 to all the way to L equals 3. And this dashed line is the size of the instability band. And as you can see, only within this, you have unstable mode. So as you can see, initially we have many modes that are unstable, but once the solitons are shrinking down, each of these higher L modes, their growth start to get arrested. Well, until they shrink to a smaller size and reflect back, L equals to 2 prevails. That's why we see all this kind of breakup. Right. And so after we do time applying, enlarge the size of the vortex cores, most of the time we see this kind of a L equals to 2 modes breaking into this kind of so-called weakly bound vortex dipoles. But sometimes we could also see L equals to 3 modes. That's been seen here. Okay. So that's about this. So all this very beautiful self-pattern, this kind of necklace of vortex dipoles is formed only just by a single point of the box, right? We shake the box a little bit and wait for some time, this appears. And this by itself is also kind of can potentially be a fully coherent evolution. In fact, we think that this dipoles, they would move away to the edge and then move along the edge until they kind of meet other dipoles, form a pair, and will go back to the center and then go back out again. So in fact, it actually could, in principle, form a persistent revival of structures. And another thing that I kind of want to bring it to your attention is that if in the case of modulation instability, the formation of this density waves is actually quantum entangled, right? Then for development of all these different angular modes, we also end up with some kind of quantum superposition of all these different angular modes if the initial instability grew all just from quantum fluctuations. That means that if this is the fully quantum instability, then so when we evolve the gas, before we actually measure these different vortex dipoles, they could be in principle be all possible angular orientations. It's only when we take a picture, right? This perturbation, this excitation get projected into one certain angle, right? And so to really prove that is experimentally very challenging, but this is also something that I'm very interested in exploring in the future experiments. All right, so after finish talking about 2 very classical instabilities, let me very quickly in the last 3 minutes talk about Langdon instability. So in this particular experiment, again, we hold the gas in a circular box in a repulsive potential. But right in the middle, we create a attracted dipole. What it does is that it attracts a lot of atoms to the center. Okay. So if nothing else is happening, then once these atoms fill the center, then that's it. No dynamics would happen. But like I said, these atoms they are in the metastable state. They are not actually in the true ground state. So if you have a lot of atoms in the center, actually you will start to have loss. In fact, this is the only loss mechanism available for our gas is 3-body loss. Basically, 3 atoms come in, 2 atoms form a molecular state, release their binding energy, and the molecule pair. The molecule and the atom will fly out. And then we'll leave the trap permanently. So right in the center, we have a 3-body loss that's proportional to density to the cube. And since the density in the center is as high as 10 times higher than the rest of the system, right? So the 3-body loss rate right in the middle will be, I write down 250-fold. Sometimes it's actually almost 1,000-fold stronger than the rest of the gas. That means that this center acts like a sink, very efficiently remove particles from the center. And what will happen when you remove particles from the center? Well, the gas will want to flow into the sink to compensate for the atom loss. And since this is a radial flow, right, and for the conservation of particle, the flow rate will become faster and faster near the center. At some point, that flow will be even flowing faster than the speed of sound. And the construction of this actually was kind of inspired by some of the studies to create animal black hole. If you have flow that's faster than the speed of sound, that means that once the phonon enters the supersonic region, it can no longer escape. So this is so-called acoustic black hole. And then there's also some interesting predictions like Hawking phonon radiation will come up coming from this horizon. But that's not what I want to discuss here. What I want to discuss here is, well, if you have supersonic flow, would that be a problem? Well, this gentleman here, Landau, says, oh, you are going to have some problems. So there's this so-called Landau's criterion for frictionless flow. If you have some obstacle that's moving across a superfluid with a speed larger than the speed of sound, it turns out that you would violate the criterion, and the obstacle can actually transfer momentum to the elementary excitation in the superfluid, which is phonons. Right? You could start to create phonon excitations. And so that means that once you fall across the speed of sound, the fluid is becoming unstable. Right? And so there are people like try to study this kind of a criterion. They take a single beam, drag it across a superfluid, 2-dimensional superfluid. Then they actually can see vortices being generated, not just phonons, vortices. And they actually found that the speed of the critical velocity is way smaller than the speed of sound. And so, so the reason, well, explained by Feynman is that, well, the critical velocity for creating a vortex is much more stringent because vortex is much easier to create. Energetically much easier to create. So there's also measurements, by taking a repulsive beam, storing across the toroidal to the superfluid, and can actually see that vortices are being generated. And so basically the construction that I have here, I do not have any obstacle, right? So again, I just have an attractive potential and everything is self-induced. The supersonic flow is self-induced. In this case, will we also see Landau instability? And so because of the interest of time, I just say that my colleague, they do the analysis, actually see that you could, find a stable solution as long as the local speed of sound never goes across the local flow speed never go across the speed of sound. But once the flow speed go across the speed of sound, stable solution just never appear, just disappear. And so we think that this would correspond to some kind of random type of instability. And so because the stable solution disappears, so we again resort to numerical simulation. This is a GP simulation. We turn on in the middle attractive potential. And then at some point, when this potential gets deep enough, you start to see all this kind of a ring structure start to be generated and emitted to the center. Of course, at later times, some other things appears, and this entire thing becomes kind of turbulence. And so if you remember seeing this kind of ring-shaped dark stripe, this is actually the ring dark solitone that you see. Okay. And so I'm just trying to say that the formation of this ring dark solitone actually coincides with the time where you start to see supersonic flow. So really, we would have this kind of a self-patterning of ring dark solitones being emitted once we create an attractive dimple inside the middle. And so this kind of this trend of dark solitones are really kind of emitted all by the kind of self-pattern by the gas itself. Okay. And so because of the time, I'm going to end my talk here without going into external details. But I'm just trying to say that I've given you kind of 3 examples of creating some dynamics in the superfluid, and we see instability forming. In one of the example, I even show that there was actually quantum entanglement coming from the quasi-particle pair production, and these are the references. And then in the end, I would like to acknowledge my group. These are my students and postdocs who did this experiment, and also I have theory support, also Siemens. Very good collaborator, providing us a lot of ideas, and the rest are kind of funding agencies. And thank you for your attention. Thank you.
Thank you very much, Chen Lung, for the great presentation. So let's start with questions from your students.
In your solitone necklace formation, how do you shape the system?
How do I?
How do you shape the system?
Well, in that case, we do not shake the system. We just suddenly change the interaction to attraction. So we do this by suddenly change the magnetic field. Yeah.
So you had this kind of the length, the atoms, 30,000 atoms, and
Yeah.
you eventually ended up with like I think 4 vortices in it.
Yeah.
So does that have to do with the number of atoms or the time you take?
Yeah, that's a very good question. So in that particular realization, the most unstable mode is L equals to 2 angular mode. So only 180 degrees. That's why you see 2. But if you increase the density, then you can shift the most unstable mode. Say, for example, to L equals to 3 or L equals to 4. So in this case, then you will start to see triangular pattern or square pattern, 4 pairs of vortices coming out, or even more. That really depends on what is the most unstable mode and what would eventually take over.
Other questions?
When you change the magnetic field, so the amount that you change the magnetic field by and the duration that you take to make that change, how does that affect the modes that you get?
Okay, so typical time scale for this pattern to form takes about tens of milliseconds. And the magnetic field, so we perform the experiment typically on about 20 Gauss, very small magnetic field. And then the amount of change is like tiny, like at most 1 Gauss. Experimentally, it takes less than 1 millisecond to change the field. So the time to change the interaction is much shorter than the evolution time. So you can basically treat this as a silent sequential of interaction.
Other questions? Okay, let me just ask one question. So in the last setup that you had with this beam,
Yeah.
where you drive this beam, essentially potential, do you expect beyond the cross potential effects or right?
That I don't know. Well, okay, so I cannot say that. Okay, so I jump out, actually, experimentally, we do see what's not seen in Gauss-Picard's equation. So, this is so if you look at the diagram here, right, so this is the flow plus the sound speed profile. And experimentally, we can also calculate the flow plus sound speed profile. This is what we get. How do we calculate sound speed? We just look at the density distribution, and then so we can calculate the sound speed. For flow, we just look at the annulus area, look at the rate of change of the atom number in that annulus area as a function of r. R is the inner radius, and so this is how we calculate the flow. And we actually see that there's all this kind of a very fast horizontal stripes coming out. And at first, it was very easy to just think that this is probably noise. But we actually take those and then take this and then do the Fourier transform. We actually see that it gave us some frequency peaks that actually correlate to the kind of solid, the kind of a defect motion, which gave us a GPE. But why is that we're seeing this in the experiment? We don't see it in the GPE. We think that these are probably related to atoms that's coming out due to discrete eye loss, and then we are detecting that. And so these, of course, is not included in GPE.
And why, how do you find that this major three body loss and not two body loss?
Because two body loss is not allowed because conservation of energy and momentum. You cannot release the binding energy at the same time have two particles.
Okay.
Yeah.
Okay, thank you. So is there any last question? Okay, if this is not the case, let's take our.